Good afternoon, everyone. We're here to discuss engineering standards and codes and also work and energy. This is a two-part presentation today about different topics. One is something that we kind of use on a daily basis, and the other is something we always use on a daily basis. So let's get started. So, codes and standards. So, why do we need codes and standards? I'm going to assume that we've heard those words before, but we may not know what they actually mean, and we may not know what the difference between one and the other is, right? And I will say that in general, codes are used to keep us safe, and standards are used to assure us that things will work together. So I'm going to start by giving us a few examples, and then we'll get into a better definition. So a couple of examples of standards is something like a credit card. A credit card, if you notice, they're all the same size, and they also have the same information on a card. That is an example of a standard. Another example of a standard is USB. USB has come about in the computer industry as a standard on how we connect things to our computer. And it has to do with this connection and the speed on which data is transferred. And at this point, actually, that has changed also because we're up to, I know, USB 3, where we started with USB 1. And even the connectors have also changed because now we also have the USB-C connectors, which are a slightly different connector than the original USB connectors. But these are examples of standards. So when I differentiate between a standard and a code, just thinking of those two items, we could see that a code is something that has actually been put into law, so we have to follow it. Whereas standards are a group of people coming together to come up with a standard so that things work well together. Some of you may be too young to remember, but in the old days of computers pre-USB, there were all sorts of different standards on how I connect a peripheral to my computer. So I'm going to go from USB, which is a fairly modern standard, to nuts and bolts, which there have been standards for a while as to how they work and how they go together. Keep in mind, prior to the modern age, nuts and bolts did not follow a standard, so they were made individually by blacksmith or something in that effect. And so they didn't actually meet a standard until, I guess, the 1800s, honestly. And a lot of those standards came into being with the advent of steam locomotives. And we started actually the Industrial Revolution, and we started mass producing things. So standards became very, very important for that. So the reason that it's important to have standards for nuts and bolts is because we have to, make sure they fit together, right? So, and now we actually have, in the United States at least, we have a lot of stuff that is still English units, and then we also have nuts and bolts that are metric units. So again, we have to know what size they are, and we have to make sure that they will fit together. The other thing that we actually have to look at is, are they strong enough for the application? So when we are picking a nut and bolt out, we have to know what the loads are going to be on there so that we make sure that they don't fail while in use. So as an example of that, there are different grades that the SAE has come up with called Society of Automotive Engineers. and that will tell you how strong a bolt is. So there are people, again, that come up with these standards and codes. So ANSI is one. It stands for the American National Standards Institute. ASTM is the American Society for Testing and Materials. NFPA is the National Fire Protection Association. And UL is the Underwriters Laboratory. And I'm sure if you guys look at anything you have that's electrical, it probably has a little UL symbol on there. And that means that it's been tested by them to be safe when used in the proper way. Similarly, the NFPA actually does standards for fire protection. So in general, if you are going to be putting in a sprinkler system in a house, as an example, it should follow NFPA 13, which is one of their standards. Now, the interesting thing, and one of the differences between standards and codes, is that many states and municipalities have taken a standard like the National Fire Protection Association standards and said, if you are building a building that meets these criteria, you have to install a sprinkler that follows NFPA whatever. And there'll be two numbers. So like NFPA 13-96 as an example would have been a code, something that was written in 1996. Of course, now we have much newer stuff than that. But what these municipalities did was they took a standard and they made it into a code. So they made it into a code, and everyone has to follow that code. So as an example of that, you guys may be familiar with building code, right? You may have heard that term. So if I am building a building in New York State, I have to follow the New York State building code. Even though we're in New York State, New York City actually has its own building code, and there are some differences as to what has to be built. So again, I took a standard written by somebody and I made it into a code. A code is a law. A standard is just an agreement. So among the things that I will say in standards, so I have for the building standards, the International Organization for Standardization is actually ISO, not really building. The second one is the Building Officials and Codes Administrators International, BOCA, they write building codes. But ISO is an organization that you'll see their ratings on just about anything, and factories and the like, which just says that it was made to their standards, right? So as such, the big difference between standards and codes is that, standards are something that a group agreed upon. Codes are something that a municipality or a governing agency put into law. That is the big difference. So I'm also old enough to remember several standards that were adopted and then actually fell out of use. And I was thinking about one of them today because something came up that I was reading, and it actually talked about a Blu-ray disc. And I know some of you may have Blu-ray discs, but some of you may know that originally, prior to Blu-ray, there were DVDs, a digital video disc. And prior to DVDs, there were CDs, which were compact discs, which were basically for file storage and for music. And these are all standards. But when the Blu-ray came out, there was actually a competing standard. And so the competing standard was between high definition HD DVD, which was being pushed by Toshiba, and Blu-ray, which was actually being pushed by Sony. And in the end, the Blu-ray won out over the HD DVDs. But now, with so many people streaming music, it's rare to even find a Blu-ray anywhere. I mean, I have some old ones around the house here, but I haven't purchased a new one in a while. And so there is something that just in the span of a few years came up as a new standard and then kind of went out of favor. But there's a bunch of standards that I could think of that in my lifetime have kind of almost disappeared. Prior to CDs, there was a battle between videotape, and the one was VHS and the other was Beta, and they were two formats that did the same thing, and VHS actually won the format war because of the fact that they licensed it to many people, whereas Beta was only made by Sony. So that was like another one that kind of came out. And one that I was discussing this weekend was actually film, because prior to digital cameras took film, and I guess the most common, most popular film format was 35 millimeter, but I also shot in what was called 120, which were larger roll of negatives. So those were out there, but there were also 110, 126. There were different standards for film. But if you bought a 35 millimeter camera, you knew that you could go into a store and buy a roll of film that was 35 millimeter film, and it would fit your camera, right? So there was nothing saying, oh, if you don't build a 35 millimeter camera, you're going to be arrested or in trouble, but you stayed with the standard so that things work together. I'm going to actually ask in the discussion forum for you guys to think of some other standards or codes, but more standards that may have come up and kind of disappeared. And I will tell you one other one that I've seen recently, because we sold my parents' house, and my father had a collection of 8-track tapes, and that was a format for playing audio tapes. And I remember back in the 1970s, we had an 8-track player in our car, but I found all of these 8-track tapes, and I have nothing to even play them on. So there is a standard for tape, audio tape, that just kind of disappeared, and no one's making an 8-track tape player, so I have nothing that I could do with these 8-track tapes that I had. So similarly, in the United States, we took a set of drinking water standards and actually passed them into a code. And what that actually did was actually ensured that throughout the United States, you can drink a public water supply and it is safe. Now, I know some of you are going to argue, but I was over somewhere else and the water didn't taste like I'm used to. And that is true. It may taste different, but it will not harm you, right? The water is safe to drink from municipal water supplies throughout this country. And that's because of these standards that became a code, and it limits the amount of contaminants in water, and has been done for the public safety. Similarly, outdoor air quality standards have been taken by the EPA and made into a code. And the purpose of that was to reduce air pollution so that we are all healthier, right? And I personally remember years ago how bad the pollution was in California. And, LA, there was generally a smog that stayed over the city of LA for extended periods of time. And California pushed for air quality laws, and they have their air board that have their own set of laws that are actually stricter than what the EPA set up. And it actually did have an effect of reducing the air pollution. And so it's a good thing. It was a good thing that they passed these laws because it did help make people healthier. So now I'm going to talk about something completely different. Energy and power. And these are two topics that we use those words a lot, and they are very important words to us as technical people and as engineers. And I'm going to actually kind of give you guys a little bit of a different outlook on them, I hope. And I have some videos that will be on Blackboard, links to YouTube videos that I would like you guys to watch. I have demos that I would normally do in class, but since we are remote, I will be giving you guys videos to watch instead. So first thing here is work. And work is performed when a force moves an object through a distance. Now, that sounds simple, but what is very important for us from an engineering point of view to consider is that I need a force and I need movement, right? If the object doesn't move, by definition, I am not doing any work. As an example, if I push against the wall of my room with all my might, I'm not going to move the wall. Well, I hope I don't move the wall. So in reality, I have not done any work because the wall did not move. So I need that movement to perform work. So I grabbed this graphic that I found on the internet and put in here because I thought it was a kind of a good little indication of what we're talking about. So as you can see, work is done on an object when a force acts on it in the direction of its motion, right? So you can see it on the left side, I have a block and I have a force and it's moving a distance d, right? Or has a component in the direction of motion. So notice on the bottom left, the force is coming in at an angle theta and the block still moves that d. So work is not done when there is no motion. So you see that force is pushing that block in the middle, but the block isn't moving, so there's no work done. Or when the force is perpendicular to the motion. So if you look at the bottom middle picture, that force is going straight up, but the block is moving sideways. So that force is not doing the work. So there's another force in play that is doing the work, but it's not that one. So on the right-hand side, we'll see the equations for this. So for a constant force in the direction of motion, my work is equal to my force times my distance, x. For a constant force with a component in the direction of motion, my work is equal to F cosine theta times x. And I will kind of just say what these are, but we're not going to focus on this in this class because this is not a calculus-based class. But for a variable force in the direction of motion, my work is the integral of f dx. And for a variable force in the variable direction, my work is my integral of f cosine theta dx. So energy, right? We hear that term a lot. We've probably used it a lot. You know, there's probably days when you say, I have no energy. Or you know, we hear the terms about the energy crisis. And I actually was in a meeting with one of the previous presidential administrations, and they were talking about energy, and they were talking about an energy crisis. And the engineer in me actually raised my hand, and I said, you know, there really can't be an energy crisis, right? I said, the problem is that the energy is not in the form that we want it to be in, but, you know, why did I say that? And I'm going to get to that in a few minutes as to why I could make that statement that, you know, from an engineering point of view, we really can't have a, quote, energy crisis. So energy is the capacity for doing work. That's what energy is, which for objects in motion includes kinetic energy and may include potential energy due to gravity and due to elastic forces. And even though I'm going to go over that here, I'm putting a link to a video which I would like you guys to watch when you get a chance, which goes into that a little deeper about those. But energy is constrained by the fundamental principle of conservation of energy, which appears in many guises, and including the mechanical work energy principle. And energy could appear in multiple forms and is expressed in multiple units. And we're going to give some energy examples as we move forward. So kinetic energy is the energy that something has when it's in motion. And it is given by the equation where 1/2 is equal to mass times the velocity squared. Right? So that tells you how much kinetic energy something has. One thing to keep in mind here is that that velocity term is squared. So if I double the velocity of something, it has 4 times the kinetic energy, because that, you know, I'm doubling the velocity, so I go 2v, and I take that 2 squared is 4. So keep that in mind when we start looking at something, and that's why when the faster I'm going, the more kinetic energy I have, but it, like I said, it rises every time I double my speed. I have 4 times the energy. Is this important? Yeah, it is, for various reasons, and one of the big reasons is also when it comes to safety. And like when I look at in cars now, as we are coming out with safer and safer cars, you know, the fact that I have to protect against higher and higher speeds is very important. Potential energy. Potential energy is the work required to lift an object with mass m to a height of h. So, and this is due to gravity. So the formula is m times g times h, where mass, m is the mass, g is the acceleration due to gravity. In metric units, it's 9.81 meters per second squared, and h is the height. Right? So we all probably understand this, because if we take something in our hand and hold it above the ground and just hold it there, it has a potential energy. When we release it, that potential energy starts changing form. We'll talk about that in a minute. And then another type of potential energy is elastic energy, and it is the energy stored in the spring when it is compressed. So elastic energy is equal to 1/2 kx squared, where k is the spring constant and x is the compression distance. So we all are probably familiar with this, because I would venture to guess that there is no one in this class that at one point or another hasn't taken a rubber band and pulled it back and then shot it at somebody, right? And what you are doing by pulling it back is actually storing elastic energy in there, right? So yes, even a rubber band has a spring rate, right, with a fairly low spring rate, but it stores that certain amount of energy. Similarly, I, as a car guy, am kind of obsessed with different spring rates in different cars. So I know that I have an older Camaro, and one of the things that is striking to me is that the spring rate for the front springs in that Camaro is 365 pounds per inch. So thinking about that, what that is saying, that to compress that spring 1 inch, I have to put 365 pounds of force onto that spring. So those are actually pretty stiff springs, and that's not kind of the normal. But depending on the car, you can have high spring rates. So why would you think that a car like my Camaro has such stiff springs in the front? And the reason is actually twofold. And one is the fact that that car has a heavy engine sitting right at the front of the car. And then also that the car was actually designed to handle well, and so did not want a lot of lean as you're going through a turn. So they put a stiffer spring rate in there. And as a comparison, I said that car had a 365 pounds per inch front spring rate. And I'm going to venture a guess that no one here knows the spring rates for their car right now. But maybe that's something else that we could kind of look up for our car, because you could probably find that information out there. But I know that, like, some typical cars, they have spring rates around 110, 120 pounds per inch. So, and as you can see, that's a big difference from that, from the 365 to 110 pounds per inch. It's quite a big difference. So again, but other cars will ride a lot better because of those softer springs. But the higher the spring rate, if I'm compressing it 1 or 2 inches, I'm storing a lot more energy also. So conservation of mechanical energy. So the conservation of mechanical energy states that the total mechanical energy in a system is constant if we have no heat transfer and no work. So what that means is that my delta in kinetic energy, so that delta means change of kinetic energy, plus my change of potential energy, plus my change of elastic energy is equal to 0. So an example that I like to demonstrate while I'm in class is to go back to that rubber band that I mentioned before. So if I take a rubber band and I pull it back and I'm holding it, right, that rubber band has potential energy due to gravity based on how high it is above the ground. It has elastic energy because I pulled it back and I'm holding it. But as I'm holding it, it has no kinetic energy. It's not moving, so it doesn't have kinetic energy. But once I release it, the elastic energy and the potential energy are then being converted to kinetic energy, right? And so as it's losing both elastic energy and potential energy, it's gaining kinetic energy. So again, the total energy of the system is going to be the same. So keep that in mind. So the first law of thermodynamics, and I say this is probably the most important thing that you guys will learn in your entire lives, is the first law of thermodynamics, because this is what governs how the universe works. So that's pretty important to me. And it states that, and it's in two parts, that it states that energy cannot be created or destroyed. It can only change forms, right? So the implication of this is that I can't create energy. All I'm doing, and I can't destroy energy, all I'm doing is changing it from one form into another, right? So remember what I said before about I had this conversation that I can't really have an energy crisis, because what this is stating is that all the energy that ever existed in the universe has always been there. And all that I'm doing is taking it from one form and changing it into another, right? So everything that we do is just taking energy from one form and changing it into another. So I have ways of figuring out how I'm doing that, but again, I'm not creating energy. I'm just changing it from one form to another. So when you think of, we spoke earlier in the semester about electric power plants, right? I'm not creating energy, but I'm taking energy from something and changing it into electricity. So if you guys remember how I did that in a power plant, conventional power plant, I take heat by burning something like either natural gas, oil, coal, or using in a nuclear plant, just using the radioactivity to heat water up to steam. And that steam then has enough energy to spin a turbine, which is connected to a generator. So I am converting the energy of that steam into the electricity, right? So I'm not creating electricity, I'm just changing forms. So that's why my statement about we can't really have an energy crisis, because all I'm doing is changing around energy from one form into another. So keep that in mind, and we'll discuss it more later. But again, it's a very important thing. I'm not creating or destroying energy. I'm just moving it around and changing it from one form to another. So the equation for this is my Q minus W. So Q is the net heat transfer into the system, and W is my net work done by the system, is equal to the net change in total energy of the system. So heat transfer into the system is considered positive. Work done by the system is considered negative, work done on the system increases the total energy, while work done by the system decreases the total energy of the system. So as an example, simple example, let's take a car, right? And for a internal combustion engine car, right, I'm going to start off with a full tank of gas, right? So I have energy in that system because I have heat energy that is stored in my fuel, right? So I have a certain number of BTUs per gallon that is stored in that fuel. I have a certain number of gallons in my gas tank, and I start driving the car. Start driving the car, and I'm burning that fuel, and I'm actually converting that heat energy into mechanical energy that moves my car down the road, right? At some point, I will have used up all the fuel that is in my gas tank, and my car will stop. It now has no energy left, right? Similarly, if we have an electric vehicle, I'm putting energy in the form of electricity that I'm storing in a battery. Once that battery is charged, I start driving. Once that battery is discharged, I stop driving. It's the same principle. So so I talked about energy, but now we're going to talk about power. So we've heard that term before, and what power is actually work over time or energy over time. So in metric units, power is expressed in watts. So when you look at anything like an appliance or a motor, it's going to be rated in watts. Even light bulbs used to just be rated in watts. When light bulbs were all incandescent, you purchased them based on the wattage they used. The more watts they used, the brighter they were. In English units, power is expressed in pound-feet per second, but a common term for power is horsepower. So when you look at like a car engine or even electric motors, they're rated in horsepower, and a horsepower is actually 550 pound-feet per second. So I'm going to tell you that everybody in this class could probably generate a horsepower for a short period of time. So if you think about it, I would say, could you lift 550 pounds 1 foot in 1 second? And you might argue, there's no way I could lift 550 pounds 1 foot in 1 second. But can you move 250 pounds, 250 pounds 1 foot in the second? And you say, oh, I could probably do that, right? But then if you actually move it 2 feet in that same second, guess what? You've generated a horsepower. So if you could move 275 pounds, 2 feet in a second, you've generated a horsepower. And I'm pretty sure that everyone in the class could probably do that. So this term is something that is knocked around a lot, and it becomes very, very important to us as engineers. And it's the word efficiency. Efficiency basically is the actual output divided by the required input. And all systems have losses associated with them. So efficiency is basically between 0 and 1, right? Or 0 and 100%, right? Depending on how you want to write it up. So that is going to tell us what output I'm getting out based on what input I'm putting in. So one of the things that makes electric cars now enticing, and the reason that we're moving towards them, is not only that they don't burn gasoline directly, but in that electric motors are actually more efficient than gasoline engines, internal combustion engines in general. And in internal combustion engines, diesel engines are actually more efficient than standard gasoline engines. And what that means is for the same amount of energy I put in, I'm getting out more when something is more efficient. So that is something to keep in mind when we are looking at things. Again, the more efficiency I have, the better it is. But I'll give you guys an example of another thing that is getting more efficient as we are moving forward, but that still has a long ways to go. Because I would say a number of years ago, photovoltaic cells, the solar panels that are on your roof, were approximately 10% efficient. So what that is saying, that 10% of the energy from that light is being converted from light into electricity. The newer photovoltaic cells are about 18% efficient. So we've gone from about 10% to 18%. And that's a significant improvement, right? But if I could get even further and get even higher efficiencies, there will come a time when you have no other choice but to go solar, right? So that's something that we should all keep in mind, that everything has an efficiency to it. There are losses associated with just about any system, with any system, and that loss could come about in a number of ways. When you look at noise coming off of a system, believe it or not, that noise is loss, right? It's losing energy because of that noise that it's making. Heat coming off a system is also loss, right? So we do not have anything that is 100% efficient. We do not have, as they call them, perpetual motion machines. So we are going to have losses with everything that we deal with. So just be aware of that as we move forward. So I hope you enjoyed this lecture, and I will be posting the next one soon. And please watch the videos that I am referring to on Blackboard, and I hope everybody has a very good day. Thank you.